Someone's already there.
Hi guys, we're gonna start in 5 minutes. Could we wait for 5 minutes? I guess. Thank you.
Hello, everybody. Welcome to this second workshop in the series called Learning Machine Learning. My name is Shyam Agarwal, and with me are my fellow presenters, Yashanani, Jeevu Lee, and Khalid Bagli. So, first of all, can everybody hear me on Zoom? Okay, nice. So, a quick question. How many of you were there with us in the Wednesday workshop? Can you raise your hands? Oh, okay. Only one, I guess. So a quick recap, what we did last time. We had talked about what machine learning is, what artificial intelligence is, how they are different. We talked about some real life scenarios where we are using machine learning. Then we talked about supervised learning, unsupervised learning, linear regression, classification, clustering, and to name a few modules, we talked about K-means, K-map, SVM, and linear regression. So good news for everybody who were not there last time. We do have the video uploaded on YouTube in the name of GDSC at UC Davis. And if you have any questions, you can ask us, reach out to us to the GDSC Discord. Today, we'll be talking about neural networks, and we'll study what MLP classifier is, how is it different from CNN, and ultimately, our final task would be to make our own handwritten digit recognizer. So let's get started.
All right, so I'm going to give a brief introduction and overview to what neural networks are. So basically, neural networks are a branch of artificial intelligence. They're supposed to basically adopt and model, sort of emulate what the brain does. And as you can see on the right, I have a small picture of like a neuron. Neurons typically they have stimulus receivers, stimulus processors, and stimulus outputs. And that's going to be more important later on throughout the discussion. But what you should kind of know about neural networks is that they're central to the. Oh. System is responding.
Can you see it now?
Oh. All right. So basically, what you should know about are we good?
Oh. I guess there's some issue with the keynote, probably.
Yeah, just press the play.
Yeah, let me share it again. The thing is,
Okay, go to share it.
isn't working. Yeah.
Just don't play it.
No.
Play with this small screen.
Can you see it now?
Okay. All right. All right. So basically, all you need to know about the introduction to artificial intelligence is that it's central to the development, what you need to know about neural networks is that they're central to the development of AI and deep learning. Again, they're supposed to emulate the way our brains work. As you can see, there's some neuron connections, firing, obviously, taking in input, exerting out input. On the left, you can see what our brain would typically look like in that kind of machine learning model. Neural network on the right is supposed to kind of emulate what happens on the left. So let's take a brief look at the structure of neural networks. So if we just start playing this video, we get some input, like let's say we're driving a car and we see something on the road or whatever, or the environment around us, or sort of something outside in our worldview. That goes into the neural network, as you can see, which is sort of represented as this box right here. And then what's outputted from this neural network would be sort of what you do, like when you're driving. Maybe you hit the gas, you change your steering, and so on and so forth. And so, as you can see, the neural network representation is shown here as a bunch of neurons all connected with the weighted connections. And so I want to just emphasize on the left-hand side, you're looking at the environment around you, you're looking at things around you, inputting that into the left-hand side of the input nodes, exerting out through the right-hand side of the neural network, an output, for example, hitting the gas or changing your steering and so on and so forth. Again, the basic components of an artificial neural network: input neuron, output neuron, and so on and so forth. Let's go through the activation and summing functions of artificial neural networks. So basically, let's say you have two nodes on the left and one output node on the right. Let's say that you have some sort of stimuli or input come in on the left. That's going to be changing the value of x1 and x2. So those x1 and x2 values are going to be maybe 1, 0, or some sort of value that you get from your environment. What's going to happen is the weight is going to have another value itself too. And you're going to multiply the weight of each node, of each edge of each node, times the value of the node and sum them together on the right-hand side. And you'll see how that works later. So as I said earlier, this is just going to help you visualize that process. You're going to get some stimuli on the left. You're going to have the weight function. You're going to multiply them. You're going to have some stimuli on the left come in. It's going to change the value of that. You're going to you're going to multiply the weight of each edge and the neuron value. You're going to add all those values together, sum them up. That's going to be what your output neuron is. And then that output neuron value is going to go into an activation function, which is right here. Is there any questions on that? And that output value is what's going to be the output of your neural network. And so basically, throughout our neural network, we're going to have these activation function, summing equation, values being done on each single neural network node from the top to the bottom with their corresponding weights and corresponding numbers. And another brief introduction to neural networks can be shown here. We have, obviously a small neural network, a bigger neural network, and even a bigger one. And the last one is really what comes into play when you're thinking about deep learning. So deep learning really is more of a more highly interconnected neural network with more branches, more nodes, and more edges. So let's build a very basic neural network. So the first thing that I want to address is the output neuron. The main question that we're going to have here is for the entire neural network is, should we go surfing today? And the output neuron is going to either have a value of yes for 1 or no for 0. Now let's move to the input neurons. We're going to have 3 input neurons and 3 questions which are going to address whether or not we should go surfing. So the first question is, are the waves good? If the waves are good, we're going to assign yes to that value of the neuron. If they're not good, we're going to assign 0. Is the lineup empty? Likewise, we're going to assign yes if it is empty, not if it's no, 0 if it's not. And has there been a recent shark attack? We're going to apply 0 to that if there has been, or no, a 1 if there has not been a shark attack. So let's say in this case that the waves are really strong. So we're going to put 1 for our first neuron value. Let's say that there are no crowds. So we're going to put 0 for the second neuron value. And let's say that there has not been a recent shark attack. So we're going to apply 1 to our first neuron value. From there on, we're going to worry about assigning the weights of each edge to our neuron values. In this case, what this is going to do is it's going to adjust the neural network by preference. So basically, let's say that you have a certain preference for the waves, whether or not the ocean is empty and whether or not there's a shark in the water. In this case, we care a lot about the waves since our weighted value is 1. We don't really care about crowds since that weighted value is 2 for that edge. And we care a little bit more about sharks since the weighted value is 4. And as you can see here, I'm not sure if you can see my mouse, but this is my mouse. But anyways, as you can see, on the edges on the right, you have 5, 2, and 4, which correspond to each of the weights. Basically, when we sum all those edges and values up, correspondingly 1 times 5, 2 times 0, and 1 times 4, we get a value. And if we subtract that value by 3, we get a value of 6. And this should be the output value of our neuron, help us decide whether or not we want to go surfing for the day. Because basically, like I said, we're summing, this is the summing equation essentially. This is where that summing equation comes in. Then what we'll do with this number is we'll take that number that we had earlier, 6, and we'll put it into the activation function in our output neuron. The activation function for this case is going to be 1 if our weighted values are greater than 0. And in this case, our weighted values are greater than 0, the summation of all our weighted values. And so, yeah, the output for activation function is indeed 1, which means that in this case, yes, we're going to go surfing. So I just want to show some practical applications of artificial neural networks. I'm sure you guys have seen this game before, probably played it before many times. So the input and output, as you can see on the left-hand side, is the environment in which the Mario guy is, looking at, observing the neural network that is, And on the right-hand side of the neural network, you can see the outputs. This is exactly what the neural network is doing in order to play the game. It's taking in those inputs, going through the neural connections, deciding which of them to fire, which of them to turn on based on the values that it's receiving, and thereby using that to decide whether or not to activate the output or not. All right, let's go through a very simple artificial neural network here. So what I want to do is show you that on this left-hand side, we have the input. So what that sees is the ground essentially, because this neuron right here, this input, it's receiving this white signal that, hey, there's some ground here you're standing on, sending that to the right neuron, the output neuron, saying, hey, you need to fire the right neuron, the output neuron, please walk right. So as you can see, it's walking right continuously. Once it receives a signal over here that, hey, once it receives a signal over here, next slide, sorry. That, look, there's a bird above you. This is a black box, it's a bird. This connection is fired, and then A is, hit. And so the Mario is therefore supposed to jump at this point, which it does. And you'll see it jumps again when this connection is fired again. This connection is now fired, so he's walking right. Now let's just look at what I wanted to do is just basically show you guys the generational progress of an artificial neural network. So first, it starts off very simply with maybe 1 or 2 neurons, 1 or 2 connections here or there. And as the model, goes through all the progressions and iterations, it builds more connections, more neurons, more layers, more hidden layers in order to achieve a better result throughout the game and be able to obviously win the game. And this is the final result of the Mario game. And so basically, another example that I wanted to show you is the adjustment of weights in a neural network. So on the top right-hand corner, you can see there's a neural network with some weights, some weighted connections. And each iteration, each time these cars are going through the path, you can see that the weights change incrementally just a little bit throughout each iteration. So once an iteration stops and another one starts, for example, here you see the iteration stops and it starts, maybe this weighted connection will change just a little bit at the end of the iteration in response to that new adjustment it's making. See, so that weighted connection stayed pretty much the same, but as you'll see, as time goes on, weighted connections change gradually and so on and so forth, and that adjusts the neural network. So I just want to ask the audience, this is a game where the car is supposed to try and go into a parking spot. Can anyone sort of guess, what are the inputs and outputs of this particular neural network, if you had to make a guess?
The inputs will probably be the distance between the car and like the nearest object in
Yeah.
all directions.
Yeah.
And maybe the output is like the driving controls, like going forward, backward, side.
Yeah, that would make a lot of sense. Yeah. In this particular case, the inputs and outputs of the neural network are the environment, obviously how close the car is to the parking spot, whether or not the car is within the parking spot and what angle it's at in the parking spot, and so on and so forth. And so I just basically wanted to show you, an example of how neural networks learn over time and the progressions that are involved in learning. So this is after, 5,000 attempts. As you could see, was having a hard time figuring out where to park. As we go through more iterations, more attempts, it gets slightly better over time. And let's just fast forward. As we get to the 310,000th attempt, you can, see that it's relatively simple. It's relatively easy for this car to just sort of park in the space without any difficulties whatsoever. And I just wanted to show you a quick time lapse of what it looks like to observe the neural network getting better each iteration, one time, one step at a time. As you can see, it's not generally speaking hitting the parking spot as much in the earlier attempts. And as time goes on throughout the later attempts, you see the car progressively getting closer and closer around the parking spot, as time goes on.
So now we have understood how the neural network works and what's the basic definition of neural network. Let's see how the neural network actually starts learning. So the example I'm going to explain to you is pretty simple, but the actual process is very much more complicated. So let's assume a simple neural network. So for a simple neural network, we'll have one input. So let me keep it as I and a simple output, right? I'm going to give the input value as 1.5. And we're going to have a weight as well. Does anyone want to give a weight? 2. Okay, simple. So what's going to be the actual output for this? Okay, wait, let me give you an activation function, which is input into the weight. So what's going to be the output for this? I mean, it's simple maths, guys. 3, right? Yeah, 3. So as we see, we have taken a random output, a random weight, and we have taken an input, which is like a fixed thing, and we got an output of 3. But this is not the correct output because the desired output for us was 0.5. As we can see, the output we have gotten is 3 and the desired output is 0.5. So there's some form of difference. So we'll try to eliminate this difference. To eliminate this difference, we're going to find the difference between them. So let me just change the name of the variables over here. I'll put this as y. The output we have gotten as 3. So the difference I'm going to do is a minus y. And another thing I'm going to do is square it out. Can anyone tell me why I'm squaring it out? Yeah, that's correct. So what we are trying to do is mean squared error. So now I've given you a simple input, but in reality, we can have multiple outputs as well, right? And this can be A1, A2, A3, like that. So if we do A1 minus y and A2 minus y and all, we can get different values. So imagine this is minus 5, this is plus 5, and this is 0. So the answer we'll get over here as 0 if we sum all of it. But which shows that there is no error and we are getting the desired output. But that's not correct, right? Because we do have a difference. It's negative 5 in the opposite direction, and the positive direction is plus 5. And our neural network is not working exactly as we want it to work. So for that reason, we try to square everything out. So since we only have a simple input and an output with input equals to y and weight equals to w, and the output we are getting as a, and y is the one we are desiring. Wait. Yeah, my handwriting isn't that great. So we're not going to sum anything up because it's just one, and we have to divide by n, and since n is going to be equal to 1, I'm just going to write as a minus y the whole square, and I'm going to call it as c. So let me show you a graph for this. So can you guys see the graph, right? Yeah. So this is the graph we get in terms of the input and the weight. And as you can see, it's a linear line, as it's a linear function, obviously. And the input, we kept it as 2, right? Oh shit. Yeah, we're gonna need some more. We kept it as 2, so it's gonna come somewhere here, right? And the output we are gonna get is somewhere here. Yeah. But our desired output is 0.5. And 0.5 is gonna be somewhere here. So our input should be somewhere here. So kind of off by the weight over here, as you guys can see. So now I've drawn the mean square error graph. As you can see, it's a parabola. So obviously it's gonna be it's a square. So obviously it's gonna be a parabola. And we've drawn it. And as we can see, when we draw the 0.5 over here, the point comes somewhere on the parabola. Can you guess what point is this? Yeah, but what point is it on the parabola? No, not the vertex. I mean, it looks like it's on the vertex, but it's something else as well. What's the vertex of a parabola? It's basically the most minimum value in the parabola. Huh? Yeah. But since I've given a very simple graph, the parabola is coming out to be very much shaped like this. But when I take like much more complicated graphs, where I have like multiple outputs and multiple inputs, just like this, then the graph will turn out very weird, like this. And that time we can't take minus b by 2 or anything, because then we have to find the minimum over here. So basically, I'm finding the minimum over here. You're very much stuck on that window. Okay, how do you find the minimum of a graph? Exactly. So I'll rewrite all the equations over here. So we have a minus y the whole square is c. A we have is I dot w. Now we're finding the derivative. Now we're finding derivative on the parabola. So where will we do it first? And our variable is a. So yeah, but what are we differentiating? W? No, we're differentiating C. We're differentiating by A. So we get is, I'm gonna do it. Yeah. And now but we want the desired result in terms of W, right? Because we're changing the weight. We can't change the activation function all the time. We can't change the activation function because it's a fixed function, and we are putting in the value of, we're changing the weights in the neural network. So how do we get it in terms of W? But then you gotta differentiate IW as well. Yeah, so we're gonna use what? Yeah, chain rule. So dA by dW, which is gonna be I. So the function we're gonna get is dW equals to dA. Yeah, it's a lot of maths, guys. So if you guys have any doubts, just ask. So we get, now if you guys remember, I took it as 1.5. So I'm just gonna put 1.5 over here. And then I'm gonna take this as 2a minus y. And a is 1.5 w, and y, the desired output, is 0.5. So what I'm gonna get is 4.5 w minus 1.5. I didn't do the maths behind it, but you guys can understand what's going on. Or you can't. If you have any doubts, please ask. Okay. So now we have done the maths. And what do we see? And this is whatever this is. We draw the line, it passes through the minimum, right? Obviously, we're trying to find the minimum. That's why we differentiated it. And the line we drew passes through the minimum. Now, in terms of finding the thing, in terms of finding the weight, we're not always going to hit on the exact weight all the time, because the neural network will not know what's the exact weight. And I'm giving a very simple equation, because the functions we are actually going to see in neural networks are going to be way too complicated. They're going to involve e raised to x and log x and all that shit. So it's going to be way too complicated. So we're going to take some w, and we're going to get some input over here, which is going to either come over here or over here or over here. Since we took 2, as one of the gentlemen said that. So what if 2 gives us here? And we're kind of off with it, right? So we all need to move around this. And so we're kind of off with it, and we're going to move around and going to reach the minimum. Now this process is going to take like a lot of time, because we're not going to know the minimum value beforehand. So for this, we can give a learning rate for our neural network. And rate can be anything if you want. It can be 0.5, 1.5, any other value you want to give. Yeah, 3. Okay. So our desired weight. So the current weight is this. Our desired weight is this. And we're going to change with the learning rate. Oh, sorry. My bad. I forgot. 3. And we're going to change it around with differential of this. And when we are going to change it around, we're going to get our desired required weight. Now, this is a lot of maths, but what's the reason behind all this maths? What are we trying to achieve over here? So basically, we're trying to determine the weight in order to get the correct output. And the process of doing this is called backpropagation. So basically, we're finding the output, first output, then we're going back and changing the weight again and again, in order to see which one is actually the correct weight. And then we are finding desired output. Now, this is a very simple example. Now we have much complicated structures over here. In terms of complicated structures, there are going to be many more equations, many more examples, and the differential equations are going to extend like, I don't know how many layers, but all these differential equations are going to extend to layers, and then we're going to get a desired output, and then we're going to change the output, then we're going to go back again, change every weight, and then we're going to come back to the output. So we have to propagate backwards in order to find our desired weight and then reach the.
So a brief mention about overfitting and underfitting. Sometimes in machine learning, when you have models, for example, if you're trying to classify 2 sets of data, you may have a simple, SVM model, say, that you're using. And if you're underfitting the model, basically on the left-hand side, it means that you're not using enough data to calibrate the machine learning model. It's not exactly using enough data to get anything out of the model. On the other hand, if you're overfitting, if you're in a situation where you're seeing overfitting happen. You're using too much data to train the machine learning model, and it's adding extra noise across the machine learning model output that you're getting. And so you're going to want to use less data to train the machine learning model and have more of an appropriate fitting picture that you're seeing in the middle.
Not even reach here. The cursor is not visible. Okay, everybody. I guess, are you guys kind of lost on like what we have been doing till now and like how is it related to the first workshop and like how are things there? So this was all the like theoretical part. Now it's like the actual fun part. So if anybody is sleeping, please wake up. Now we are actually going to understand CNN, MLP, how is everything related, and our final coding process. So first of all, we have been talking about this circular thing. Can somebody tell me what this was called? Anybody? Little loud, please. Yeah, it's called neuron. This is called node or neuron. And I'm just adding another terminology to the same thing. We also call it as perceptron. This thing is also known as perceptron. So what we are doing over here is we are giving it some input. Let's say x0, x1, x2. Each of these inputs have a weight attached on the edge, which is like W0, W1, W2. A quick recap or a flashback of what happened in the first workshop. In first workshop, we talked about a simple example of a data where we were classifying apples from bananas. So the problem we had was we are working in a grocery store. We have been given the task of like we have a huge pile of fruits and we have been asked to classify which one of these are apples, which one of these are bananas. So I guess many of you are attending this without attending the first workshop. So give me some examples of like features that distinguish what apple is and what banana is. Yes, that's a good one.
Color.
Definitely. I mean, okay, never mind. Okay, Zoom people. Zoom people. Okay, everybody. There are so many features like the hardness, the color, the weight, the shape, the size, the length, and so on. But for the sake of simplicity, we are talking about only two of them. One of them is color and one is hardness. We all know that our data would look something like this, right? Because we know the more the red something is, the more likely it's an apple. The more the yellow it is, more likely it's a banana. Similarly, the softer it is, more likely it's a banana, and the harder it is, more likely it's an apple. So this would be my region of apple, and like my bananas would be represented by this. And last time we saw multiple algorithms to classify this, and the basic purpose, I guess, we did three different models to do the same task of classifying apples from bananas. And the basic role that the machine was doing was to find this linear line which was separating our data on both the ends. Is everybody good with like understanding what I'm saying till now? Okay. If you have any questions, feel free to raise your hand or ask, because somebody is monitoring chat as well, and we can answer your questions here as well. Okay. So if you remember, in the first workshop, I also discussed the idea of weights, where we talked about that every feature is not as important in deciding what is an apple or what is a banana. For example, you might find a very unripe banana. You know that unripe bananas are hard, right? So if we are dependent on this kind of parameters, and my machine is thinking that hardness is an important parameter, more important than color, then maybe my machine would say that a banana is an apple. But that's not true. So we need to determine how important a particular feature is, due to which we'll have to rescale our values of a parameters. So this is the weights that we were talking about since the beginning, that each of these features have a particular kind of importance attached to them. And that's what we need to kind of determine to reach to this end of like having this function. So what my perceptron is doing, these two things basically. Firstly, it's summing up all of them. It's doing x0 times w0 plus x1 w1 plus x2 w2. And it's also adding a random constant, which we call as bias. And I'm using the term B for that. Now, what my perceptron does after summing it up, there's something called activation function, which we were talking about, but like probably you guys are not yet sure what that means. So you can think of an activation function as a barrier. So what happens is that I have this amount of input. This flows into my neuron, but what will my neuron output? We all know in computer science that absence of current is represented by 0 and presence of current is represented by 1. So basically current has some voltage and current values, but what we are outputting is 0 or 1, right? So that's a similar idea over here. My sum is some random value, but what I'm outputting is something dependent on my activation function. The simplest activation function we can think of is maybe sign. Not SIN sign, but SIGN sign. So if this sum is n is equal to this, and my n is greater than or equal to 0, maybe my function outputs +1. If n is less than 0, my function outputs -1. +1 represents one of these, and -1 represents one of these. So just to sum up how like things are progressing, and like how the things that we did in first workshop are related to what we are doing right now, is that we are solving the same problem which we solved by using different models like KMeans, KMap, and SVM. But now what we are doing is we have this input. We are attaching some weights, giving it to the perceptron. Perceptron finds the sum. It passes it to the activation function. We get these two values, which basically means our result. We have our result. But the thing is, we always have two kinds of data. One is the testing data. One is the training data. Because firstly, we need to train the algorithm to work and like give it some opportunity to understand what the situation is, and then we can give it some random thing to like predict for us. So we already have some data with us that's corresponding to like what the correct answer is. So we just talked about what cost function is, right? That C that we were talking about is actually known as cost function, the mean squared error. And our goal is to reduce that error using the technique that we just discussed about gradient descent. So what's happening? A quick review: input, weights, perceptron finds sum, we pass it to activation function, we get some answer, we find the mean squared error, we use gradient descent to reduce the error, and we do back propagation to come back to this point. And again, this process repeats until we have this linear line with us. Is everybody clear with what's going on till now? And like, is everybody kind of like little bit confident, like what we have kind of studied till now is summing up and like we are actually leading to something that's very big and like very huge in the end? Any questions, Zoom people? Okay. Now, my question is that, is there a flaw or like any limitation over here that's stopping us? Like, why do we want to go to MLP or CNN? Don't we have like everything that we wanted to have? Okay, let's be more concrete. Is there a limitation of like the variety of problems that I can solve using this approach? Speak a little loud then. Okay, so the issue is that all the problems are not linearly separable. The thing is that over here we have a line separating both of them. Even if we have like multiple features, like 3 dimensions, I can assume that I have like a z-axis and all my data points are being represented as in like 3D space, and a plane can divide both of them. That still works. But the thing is, how about classifying a data which looks something like this? Wait. Which looks something like this, and some of the data points are like this. So instead of having that linear line, my goal over here would be to get a line that is non-linear, probably something like this. If you observe what the sum function over here was giving us, this thing, this sum function can take only limited values. Maybe it is something like ax plus by plus c. Maybe it is something like ax plus by plus cz plus d. Can somebody tell me if this is the equation of? I don't remember. This is the equation of? I mean, high school geometry. Ax plus by plus c is the equation of? Huh? Yeah, exactly. It's the equation of a line. How about this? Ax plus by plus cz plus d is equal to 0. Can you show me the Zoom?
Yeah, no one asking.
Zoom people, can somebody tell me this is the equation of? Nobody knows. Plane, definitely. This, I mean, this is simple high school math. Okay. Similarly, we can get like increase the number of dimensions and we'll get some things in like 4 dimensions, 5 dimensions, 6 dimensions, but we won't be able to visualize them. But we collectively call them as hyperplanes. Okay, sorry if that wasn't covered in high school. I didn't know that. Okay. Okay, so the thing is, now we see that this single perceptron is of not much use to us because most interesting machine learning problems are not as simple as classifying apples from bananas. They are something more complex, like the figure we just saw over here. So that's why we are talking about something called MLP. Okay, we have been advertising that we'll talk about MLP and CNN. Let's see who knows the full form of MLP. Don't Google. These two people are already Googling. Okay, can you see something with P over here? Okay, so P is perceptron. How about ML? No, it's not a machine learning, unfortunately here. It means multi-layer perceptron. Multi-layer perceptron. Nice, nice. Zoom people, are you all good?
Yeah, they got mutual.
Okay, never mind. It's not mutual language processing. It's not machine learning perceptron. All it is multi-layer perceptron. So now what we are doing is we have our input. We have this kind of black box, which we'll just talk about what multi-layer perceptron is, and we are getting an output. If you realize the problem that we are trying to solve today of handwritten digit recognition, that's also a non-linear separable problem because let's say my image is like image of the number 8 and I want my machine to tell me that this is 8 actually. So let's say this is 28 by 28 pixels. I'm not so good at fast multiplication. I just learned the number. This is equal to 764 pixels basically. Everybody? Oh, I mean, I can, okay, just to save time, I learned it. Okay. Okay, it's not 764, it's 784. So we have 28 pixel by 28 pixel of an image, which means that I have like 784 pixel values. Now my input would be an input layer of 784 nodes because I want to give 784 pixel values to my machine. Does that make sense? Does that make sense?
Yes.
Then I'll have some hidden layers with me. In our example, we are using 64 hidden layers. Definitely, there are ways to find out which number should be the best for the number of nodes in hidden layers and like how many hidden layers you should have, but we won't focus in this limited time on that part. So we have some hidden layers over here. Each of these are connected. Now, who is gonna tell me how many output layers should I have? Sorry, how many nodes in the output layer should I have? I've just made 2 hidden layers. It's like not a concrete value. Like I've made, this is my input layer. This is my hidden layer 1. This is my hidden layer 2. And then I'm trying to make an output layer over here.
The more hidden layers you have, the more accurate your results will be. Is it not necessary?
Not really necessary because I mean, technically it's the same kind of an idea as we saw about overfitting. The more you fit your data, probably the data is like this and you overfit the data so that the curve actually turns out to be this. You can pretty much be sure that maybe this won't measure everything exactly for you. So there's kind of a balance everywhere. That's why we never, when we implement machines, we don't tend to have like infinite number of hidden layers. Who is going to tell me how many nodes should we have in our output layer?
Not me.
2? Not really.
Wait, bananas and apples.
No. We are talking about the actual thing that we are here for. Classifying the number. Why?
One.
No.
No, I'm asking you.
Okay, let's think. What was the question? The question was, I will give an image to my machine and the machine should tell me what digit was written in that,
Yeah.
right? So machine should tell me what digit was written in that. How many digits are there in the numerical system? 10. So there are 10 outputs. So basically what I'm trying to get over here is that my machine should give me something like these 10 values where it would kind of tell me some probability kind of numbers. Like my machine would give me maybe 0.1, 0.5, 0.05, 0.05, and then like maybe all zeros, and then 0.8 and 0. So this would basically mean that my machine thinks the highest probability of it being this number 8 is the most. Does that make sense? Zoom?
No. Not quite. It's like mental.
Okay, let me just try to do that once again, so that otherwise there's no point in like writing the code without understanding what we are trying to do. Our goal is, here is my machine. Yes. Over here, I'm giving an input like an image. Let's say the image has any number. Let's say the number 8 for no specific reason. Then I'm assuming my image is 28 pixels by 28 pixels, which is 784 pixels. High school math, which is 784 pixels. So basically I'm giving 784 inputs to my machine. We have some hidden layers because we just talked about the fact that we want to get something like this. Because the single model was only able to give us something like a line or a plane or something of the same generalization in the higher dimensions. Okay, that's why I have some hidden layers, which my machine has some hidden layers. Now we are talking about what's the output. The output is one of these digits because the machine should tell me which digit it thinks am I sending it to him. So I will get something like a vector, not necessarily a vector, but like these 10 values, where my machine would be like probably 0.1, 0.05, 0.05, then all zeros maybe, and then 0.8. Basically what I'm trying to say is the maximum value that I get over here, I would say this is corresponding to the digit that I have. Like this value corresponds to digit 0, digit 1, digit 2, digit 3, digit 4, and so on up to digit 9. Does that make sense now? Yep. More than what? Oh, I mean, that's what we are trying to do. We are just like making an algorithm that has handwritten digit recognition. So we'll just give it images, yeah. Like images of one digit at a time. That's why it's not handwritten number recognition, but like digit recognition. So now we understand why do we need multi-layer perceptron? How is it related to a single perceptron, right? Now we'll talk about what finally convolutional neural networks are. Convolutional neural networks are very similar to multi-layer perceptrons. The only difference is that some of these hidden layers are also known as convolutional layers. Some of these hidden layers are also known as convolutional layers, and their purpose is to predict some patterns by filtering our images. I'm pretty sure that doesn't make any sense. By filtering and like making some patterns. I mean, it's very similar, kind of. Okay, never mind. So let's see some slides that might help us in understanding this. So initially what I said was that what my convolution layers are doing, they are filtering my image to predict patterns. Let's first talk about what do I mean by patterns. Patterns can be anything as simple as a geometric shape or as complex as an entire organism. For example, over here, we can predict things like edges, and then I'll call my filter to be edge detector. Just like over here, if you can follow my mouse. Similarly, as we go deeper into neural networks, our network can even detect something like our sense organs, eyes, ears, nose. And even further, if we go into deeper neural networks, we can even predict the entire organisms. For example, in this image, the filter is able to recognize what circles are. In this image, the filter is able to recognize what corners are. This image, the filter is able to recognize the entire figure of dog, and over here, the entire shape of a bird. Okay. Is everybody clear what pattern means? It's the same colloquial meaning of like finding some kind of associated features, right? Now, who will tell me what a filter is? I mean, the colloquial meaning of filter. Okay. Anybody else? Okay. How many of you take selfies? How many of you take selfies, apply filters, put it on Instagram, and stare at them for getting many likes?
Yeah, just like change the picture somehow.
Yeah. So if you guys take selfies and apply filters, congratulations, you have been using CNN for a long time now. This is what we basically mean by different filters. Now let's see how we can like change such an image to this or like any of these variations by using a filter and like what that filter basically means. Don't get shocked what I'm going to say. I'll try my best to explain this. A filter can be considered as any 3x3 matrix. And what I'll do a simple operation. If you see, this is my filter over here in the middle of the screen. What I'm doing is I'm going to place this filter over this 3x3 edge of my initial image. Firstly, to explain what this image is, every image can be encoded in terms of these intensity values. If you see wherever I am having a zero, wherever I'm having a zero, the color is white. Wherever it is 1, the color is dark red, and anything in between is like along the continuum of like more red or like less red. Can you see that the digit 7 is basically being represented by these values over here? Can you see this 7? The shape is 7 and the corresponding values. So that makes sense that like we can convert this data that we have, like the image that we have, into some data, right? Now, what I mean by filtering is I'm taking each of my 3x3 filters, putting it on the top of my image, multiplying their corresponding components, adding them up, finding the average. Let's actually do that. Okay. Let's say my image, like similar to how my 7 looked. Let's say this looks something like some random numbers: 3, 2, 4, 1, 6, 2, 8, 9, 4, 5, 3, 2, and so on, right? Let's say my filter at this point of time is some numbers 1, 2, 3, 3, 2, 1, 4, 0, 2, anything at random. So the operation that I'm talking about right now is you take this filter, put it on top of this, multiply the corresponding components, add them up, find the average. It's a very simple thing. Add the components up. Let's go through how we'll do it. We see that this is 1, this is 3. This is 1, this is 3. So I'm multiplying 1 and 3, which is 3. 2 times 2, 2 times 2 is 4. Then 3 times 4 is 12, right? Similarly, 3 times 1 is 3, 2 times 6 is 12, 1 times 2 is 2. And similarly, we'll add all the corresponding values. You guys see what values I'm kind of multiplying together? Then I'll add them up, divide them by 9, because I want the average of these values.
Isn't that a 4x3?
Yeah, 12.
So how are you multiplying it with the 3x3?
Oh no. So basically what I'm doing is I have this 3x3. I take it, multiply with only this part.
Oh,
Find the sum, find the average, and now I store my average. And now I store my average in a matrix of the same size. The size of this is not changing. This was 4 by 7, right? So I would still have a size 4 by 7. But whatever result I get from this, let's say I get 3.3 maybe, I would store my 3.3 over here. Similarly, I will slide this small matrix over here, do the same operation, and store the result over here. And similarly, we'll continue the process until we get the value for all of them. Is everybody clear with that? What operation I'm doing? Okay. So this might seem like really abstract and like, what are we basically achieving by doing all this? But we are doing something really kind of, okay, let's see. So this is what I was explaining. Let's say this is my filter on the top right of the screen. I'm taking my filter, overlapping it with the first 3x3 matrix, finding the sum, storing the value, and like keep on doing it all over. Now the thing is, what I was saying, it might seem abstract. How is this even doing anything for us? But if you'll actually try to do this, and if you have an image like this and a filter like this, like a 0, 0, 0, 0, 1, 0, 0, 0, 0, the final output that you'll get is something that has no change in it. Similarly, if you'll change your filter to be something like this, 0, 0, 0, 0, 0, 1, 0, 0, 0, then you'll see that your entire picture has shifted by 1 pixel. And this should make some intuitive sense as well, because technically we are multiplying all the components together. Since my left and my center is 0, they have no contribution at all. My right has 1, which has a contribution, and all this value gets shifted and like placed in that particular cell. So technically everything from the right is going a little bit towards the left. That's why it's getting shifting left by 1 pixel. Does that intuitive sense make like everybody is feeling that thing? Okay. Similarly, there are like different filters. Like if you have a filter like 1/9 everywhere, this will blur your image. You can sharpen your image by using a filter like this. And there are like multiple filters. This is a particular Sobel filter, which you can use to find a vertical edge. I can try to make you understand like how we are getting a vertical edge, that it doesn't seem abstract. If you look, the left-hand side and the right-hand side are almost the same, right? Just a negative sign difference. So what we are doing is, if you look the image over here, there is not much difference of color. So when you place your matrix over here, add the components, the final result would be 0, because the left and the right, there's no much difference of color. That's why it's black everywhere over here, because it's all 0. However, if you look near the tie region, over here, the color is vastly different. So you get something along that edge where like the color on both ends are different. You won't get a 0, rather you'll get some other color, like some other value, which is represented by this edge. Similarly, this matrix can be used to find horizontal edge, and that's how you transform these images into different edges by vertical and like horizontal edges. These are just examples. So for our case, if we would have like been filtering our image number 7, we can use like different filters for edge selection, the curve selection, and things like that. And these are like some examples of different kinds of filters that are being used to filter your images. Okay, so the basic point. Okay. Okay, so the basic idea behind all this was to just tell how I can use my CNN model to basically filter out my images, get something simpler, and then I can pass those inputs to my machine and get my 10 outputs. Okay, I'm so sorry, the time is like little up, but now we are finally doing the fun part, the coding. Can you all open your laptops and open Google Collab? So Google Collab is like a Google feature where you can write and execute your Python code. And the best part is that you don't want to like install any other IDE or anything specific to do that. It's a web IDE. So is everybody good? Okay. So firstly, what I'll do is I'll install something called MNIST. MNIST is basically the data set of these digits that we'll be using for our purposes. I can just run it to install it. I'll create a new code chunk. Firstly, I'll import my MNIST. Then I'll import NumPy as NP. NumPy is basically a Python library which offers you a lot of mathematical functions. Then we import matplotlib.pyplot as PLT. Matplotlib is Python library which gives you interactive features like making different kinds of plots. Last time we talked about like dividing training and testing data using train test split function, but this time we won't be doing that because MNIST gives us other functions to achieve the same purpose. So I say my X train is MNIST dot train images. My X test is MNIST dot test images. My Y train is MNIST dot train labels. And my Y test is MNIST dot test labels. Is everybody with me? Okay. Can you all tell me a function which I can use to print the size of my arrays? Size of my X train, X test, Y train, Y test. Yes, Kent, you're right. I'm printing my train data set size. I can use the shape function xtrain dot shape. Similarly, I can use my Y train dot shape. In order to print my test data set, I can print my X test dot shape. I'm printing my Y test dot shape. Let's just see what the output is. Okay, so oh wait, extra parenthesis. Where?
Oh, not shape is not.
Oh, yeah, it's not a function. Okay, so I see that this is the size of our data set. Now what we can do is we can randomly print some of our Y values to see that everything is like digits only. So just randomly I'm printing 0 to 20. Let's see what we get. Okay, so we see that these are all digits from 0 to 9. Now I can print my X train 0 to see how my particular data looks like. So the thing is, just like I showed you on the slides, the number 7, we would have been actually able to see a particular number over here, but the like it kind of seems like it's number 5 because it's like going here, coming down, like kind of a curve and coming back. Can anybody see that? It's number 5. It's looking like number 5, like this. I mean, I can do this a little bit. Is it looking like number 5? 5. Okay, good. But the thing is that as the data is being wrapped to the next line, it's not properly visible, but we still have some idea that it's number 5. Now what we can do is we can use a plot and we can give it the title of our 0th element, and then I can use plt.imShow, which basically plots the actual point for us, and I'm plotting point number 0, and I can tell it map it to great. So if you see, actually our data also looks like this, the 5. Is everybody good till now? Okay. Now we'll see the rest of the code.
Okay, so finally we're moving on to
Can you show
train.
the code again?
Oh, sure. Which part?
The top trace.
Yeah, sure. So we'll start actually training the model, our MLP model. Because of the complexity, we're not gonna do CNN model this time, but pretty sure there are many tutorial video documents on the internet, so I refer to that. Anyway, so first we are gonna use a sklearn library. Import Fire. So like we're gonna use sklearn to use this MLP classifier, and before we actually feed into classifier, we wanna reshape whole data set, which means okay. So in previously, when we go see the shape of the data set, for the trained data set, there was 60,000 of numbers, and each those numbers are in 2 dimension. But we're gonna convert this 2 dimension into 1 dimension. Basically, flattening this to the array that Sham just printed out, right? So this is what this xtrain dot reshape -1 means. And for next, we're gonna basically do the same thing for x test data. And we are gonna declare the model. Fire goes to, and we will decide some parameters in here. So for example, to find the minimum points, like minimum loss, we're gonna use this optimizer algorithm called Adam. So we have to tell that to decide that as a parameter, and activation function, which you should know basically. We're gonna choose a ReLU. And we also have to give what hidden layers that we're gonna use, how many number of hidden layers or how many nodes should be in each layer, which we're gonna just use 64 for the yeah. So this means that we're gonna have 2 hidden layers, with each layer will have 64 new nodes. And next, this is the process that we're gonna actually train the model by feeding the xtrain data and the answer, which is ytrain. So we are giving data and the corresponding label so that the model can match the answer, right? And if we run this, here. Oh, sorry, typo here. It should be sizes. Oh, and typo again. Okay. And as you see, it won't run quick. It will take like about 1 minute to 3 minutes. So in the meantime, we're gonna just type a next step. So if this model runs properly, we should be able to get some predictions from the model, right? As the model already learned how to classify handwriting numbers. So we're gonna use this predict function and feed x test, which is the test variable that we got in top here, right? The test batch of images, and there are 10,000 of numbers with each 28 times 28. So basically it's same size. It's a train. And after prediction, we want to see, we can try to see what does this prediction contains, just to check. And also after we train the model, we want to measure the accuracy of the model. So we will be implementing the like really simple accuracy algorithm here. So what we are going to do is we're going to compare the Y test number and prediction number. So if those numbers are same, that means that model gave us the correct answer, right? So, and those answers should be in prediction, and the correct answer should be in the Y test. So that means, as I said, if these two numbers are same, then we will gonna add 1 to accuracy. After these iterations, we will see the results. By dividing all this accuracy by the number of test data, which was 10,000, but for just to make sure, I'm going to use NP shape of first number, which is number of data in the test, and by multiplying that by 100, we can get the percentage. Yeah, and the training is still running. Yeah, it's pretty much random. Sometimes it takes like 4 minutes, 5 minutes, but oh yeah, and at this point, if you have any question, feel free to ask. Is there any guesses like why these are taking so long? Zoom people. Okay. Do you remember that we made 64 neutrons for each hidden layer? So that means, and also we have input layers has 28 times 28 perceptron, right? Was that 684? 784 perceptrons, right? So, and all those 784 perceptrons are connected to 64. And again, 64 are connected to all of the 64. So that's like, yeah, millions or whatever number. Yeah. And yeah, and those processes are repeated, and that's why it takes so much time, but we're finally done. Let's go run. As you see, these are what the model returned us. So basically, it's a guess of model, right? So could be the first one could be 7, and second one could be 2. And let's compare and see the accuracy. Okay, so we got 96.27% of accuracy, and you guys might got different values. but this is whatever I got. And should we,
No, just do the
everything, okay. So let's try by our hand by actually drawing our own number. So first, I'm gonna import the PIL. And I'm gonna just fill out this part later on, but I'm gonna just try to finish code everything. So this line of code is to convert all the, if the image is 3-dimension, I'm gonna just convert to 1-dimension. This is what this line of code is trying to do. And we're gonna see dimension just in case. And with title, we're gonna plot the whatever we are going to draw. Okay, so finally, we're going to draw our own image. So can you all go to, yes, I'm gonna send you a link to the online drawing so that we can see same screen and work on drawing. Okay, are you guys all in the drawing page? I assume so. Okay, cool. So first, click on this white sphere in the left hand of logo and change this width and height pixel to 28 and 28. And before you press OK, press this black box here. And yeah, it's really small. So press this positive to zoom it. And change the radius of paint to, when I tried it, like 2 is the best. So I'm gonna just use 2. And draw whatever number that you like. What should I draw?
6.
6, sure. I will try to draw my best 6 that I've drawn in my life. Is that 6? Thanks. Okay. So after you draw.
Stop share and you don't do that. Go to file.
Oh yeah, okay. Okay, then you press this download button and export it. And which one? Let's pause here. So one I double this here. And when you download it, can you import that file to your drive? Can check again. Sure. Okay. So this is oh, it's really small, but this is the 6 that I just wrote. Yeah, it's 28 times 28 pixels. So like that. How can I go? Oh. And when you go back to here, press this file button and press this Google Drive file button. And this will basically connect your Google Drive files into this Google Collab. Yeah, it won't copy whole thing, but it will just copy like informational files into it. And after the process is done, it should show Drive, My Drive, and wherever the file you copied, you just find the file that you just made and press this 3 dots option and press copy path. And into this open brackets, just paste it, and that should run. But, oh, sorry, I should have import image here. There you go. Yeah, everyone following? I know it's a long process, but we are near to the end. So as we can see, we imported the image properly. We're now going to convert this image like we did in previous steps. During the train data or test data, we reshaped to 1-dimension array, right? So that's what we are trying to do again. And ask the model to predict the value by feeding in to it. And
Just a quick clarification. If this doesn't work, don't assume that the algorithm is wrong, because when we were kind of trying on our own, I tried this 3 times using my handwriting, and all the 3 times the result was negative. He tried it once, but it's my handwriting, so that's like the worst in the world. So beware. Yeah.
yeah. Shoot.
Not D.
Oh, sorry, yeah. There you go. And finally, when we print our prediction, some people will get correct answer and some people might get wrong answer. But I got correct. Yeah.
Chris wants to see the open again.
Okay, sure. Yeah, basically that's it. Thank you for following this long code line.
Thank you very much, everybody, for staying with us so long. We would share this code on Discord. So if you were not able to like copy along, that's totally fine. We will post the video on YouTube. So if you miss any of the things that you want to see again, you can do that as well. We have another workshop, which is related to Bootstrap this coming Tuesday. Which hall?
Virtual.
It's a virtual workshop. So check out GDSC Discord for that. Thank you very much for staying with us. And if you have any questions, feel free to ask us. We are here only. Thank you.
Thank you.
Have a great day, everybody.